After the completion of general tensors required for the study of general relativity, from today we are going to start the first and the foremost important chapter of general relativity, and this is actually Einstein's theory of gravitation. When you talk about general relativity, basically it means we start from the law of gravitation provided by Einstein. Okay, so this is the first chapter of general relativity, you can say. But to know about the Einstein's theory of gravitation, first of all, you will have to know two basic facts which will be needed in discussing the Einstein's theory of gravitation. So in this lecture, we are not going to directly see the Einstein's law of gravitation. But before that, in this lecture, our discussion will be regarding a very important tensor which is called material energy tensor or energy momentum tensor. In fact, this material energy tensor or energy momentum tensor, which is also known as energy tensor of matter, this is a strong mathematical tool in terms of which we develop Einstein's theory of gravity. So, I have planned to introduce you regarding this tensor in this lecture, and after that, in the second lecture, we will see the proper theory of gravitation provided by Einstein. Okay, and we will use a particular unit system of units which is called relativistic units. This is for simplicity. You are aware of SI unit. We can develop Einstein's theory in SI unit, but it is more convenient now to introduce you a system of units which is called relativistic units. Actually, the use of relativistic unit is, as I have told you, most convenient in dealing the problems of general relativity. Okay. In fact, when you talk about relativistic units, what will be the basic units, relativistic units for the three fundamental quantities: mass, length, and time. Actually, in this relativistic units, it is assumed that the unit of length is same as that in SI unit, and the SI unit of length is meter. So in relativistic unit 2, the unit of length is assumed to be meter. Okay. But what about the units of mass and time? In fact, in this relativistic units, the mass and time are so chosen that the gravitational constant g and the speed of light c both equal to 1. In such a manner, we take the values of mass and time. So you can say that in relativistic unit, both the universal constants c and g are equal to 1. It is assumed. So whenever in our calculation there will be c, we will take its value 1. When there will be g, we will again take its value 1. Okay. But in SI units, the value of c is what? This is 2.998 times 10 to the power 8 meter per second square. Meter per second or meter second inverse. And the in SI unit, the value of g is 6.67 times 10 to the power minus 11 meter cube kg inverse second inverse 2. These are the values of these two fundamental constants in SI unit. But when you talk about relativistic unit, you will take C equal to 1 and G also equal to 1. Now you can see how these SI unit for mass, length and time, and the SI unit, and the relativistic unit for mass, length and time are related to each other. As I have told you, in relativistic unit, the unit of length is taken same as that in SI unit. So if we consider that this small l represents the unit of length in relativistic unit, a small m represents the unit of mass in relativistic unit, and this small t represents, or you can say this is the value of time in relativistic unit. Okay, and at the same time we also consider that in SI unit the unit of length is capital L, unit of mass is capital M, and unit of time is capital T. Then this capital L, which is the unit of length in SI unit, that will be same as that in relativistic unit. That is, this capital L will be equal to a small l meter. Okay. But what will be the relation between the units of mass in SI unit and in relativistic unit? Actually, this capital M, as you have assumed, it is the unit of mass in SI unit, and this small m is the unit of mass in relativistic unit. This capital M is given by C square over G times M. And you know the value, the exact value of C is 2.998 times 10 to the power 8 meter per second. So this much square and divided by this value of G. And when you will simplify it, you will get that this is equal to 1.349 times 10 to the power 27 m. M is the unit of mass in relativistic unit. Okay, so if you know the value of mass small m in relativistic unit, and when you will multiply it by this number, then you will get the value of that mass in SI unit. Okay, and this capital T, you know, this is unit of time in SI unit, and this is related to the unit of time small t in relativistic unit by this relation T over C, and this will be T over this much, and so this capital T will be equal to 3.335 into 10 to the power minus 9 times small t second. Okay, actually in our calculation in dealing with the problem of general relativity, we follow a relativistic unit. Okay, and for convenience, and that's why I have introduced you the relation between the SI unit and the relativistic unit for the three basic fundamental quantities: length, mass and time. Okay, and I hope you have understand it. But I have told you that the basic aim of this lecture is to introduce you with a very important tensor which is called energy momentum tensor or material energy tensor, or it is also called energy tensor of matter, because Einstein's theory of gravitation needs its idea. Okay, so before dealing the problem of Einstein's theory of gravitation, we will learn about this energy momentum tensor. Actually, you know, the physics has been developed on the basis of some of the important conservation principles, and among those conservation principles, basically the conservation principle for mass and energy and momentum are very important. Okay, in fact this energy momentum tensor deals with the conservation of mass and momentum. And this tensor can be discussed in the absence of any external field under which the matter is subjected, or it can be discussed also in the presence of the external field. Actually, in this lecture, we will see the concept of this energy momentum tensor in absence of any external force field. Okay. But in our forthcoming videos, when needed, we will also learn about the energy momentum tensor in presence of external force field like electromagnetic field, like gravitational field, etc. Okay. So now let us try to know about this energy momentum tensor. Since this tensor is related to matter in particularly in absence of the external field, so first of all we will define it, and after that we will know some of its important property. And for this, let us consider that this rho 0 or rho naught represents the proper density of matter. When you say proper density, you have an idea of a special relativity. It means you are talking about density, the material density in a coordinate system which is at rest. Okay. So in a rest frame, the density of matter is rho naught, and so it is called proper density. Okay. Now, if the matter is in motion, its motion is discussed in terms of its velocity, in terms of its acceleration. Okay. But first of all, we consider, and during the motion, the coordinates, the position coordinate of the system changes. So definitely, if you consider that this x sigma represents the coordinates of a point, then while the matter is in motion, this x sigma will change with position. So this quantity dx sigma by ds, ds is elementary distance. This quantity actually refers the motion of the matter in a field-free region where no external field is acting. Okay. In fact, we define the energy momentum tensor as a tensor of second rank. It may be a contravariant tensor, it may be a covariant tensor, or it may be a mixed tensor. Okay. So if you denote the energy momentum tensor by this symbol, T superscript mu nu, then you can say that this is a tensor of second rank, and it is a contravariant tensor because here mu and nu are both contravariant indices. And in relativistic units, this energy momentum tensor or the material tensor is defined by this equation. You have to remember it. T mu nu is equal to rho 0 dx mu by ds times dx nu by ds. This is the basic definition of this energy momentum tensor. And you have seen that this rho 0 denotes the material density in rest frame, or you can say this is the proper material density. Okay. And as I have told you that in general, any of the tensors which may be a contravariant tensor like this T mu nu, or a covariant tensor which can be written as T subscript mu nu, or a mixed tensor. So this energy momentum tensor may be a contravariant tensor, it may be an associated mixed tensor, or a covariant tensor. Okay. Now you have studied in general relativity. You can watch my video on not general relativity but special relativity. how the density of a material varies with respect to the motion of an observer. So if you consider an inertial frame which is moving with velocity v, okay, then in that frame the material density is denoted by the symbol rho, and rho 0, you know, it is the material density in a frame relative to which the material is at rest. Okay, so if the frame is moving with a velocity v, then this material density is rho, and if the material is stationary in a frame, then the observed value of that density is rho 0. And you have studied in a special relativity that this rho and rho 0 are related by this relation. Rho is equal to rho 0 divided by 1 minus v square over c square. But I have told you that now we will write our expressions, our equations in relativistic unit. And just to have seen, in a relativistic unit, we take c equal to 1. So when you will write this expression in a relativistic unit, you must take c equal to 1. And therefore, we will write simply rho equal to rho naught divided by 1 minus v square. 1 minus v square. Okay? I think you are getting the things. But you know, in Galilean coordinates, this ds square, which is actually line element, that is given by minus dx square minus dy square minus dz square plus c square dt square. You can also write by taking positive sign before dx square, dy square and dz square, and negative sign before this last term c square dt square. But again, in relativistic unit, we will take c equal to 1. And that's why you can say that this ds square is equal to minus dx square minus dy square minus dz square plus dt square. Okay. Now let us divide this equation by dt square. So LHS will be ds by dt whole square, and in RHS there will be minus dx by dt whole square minus dy by dt whole square minus dz by dt whole square, and in last term dt by dt square will be equal to 1. But you know that this dx, dy, dx by dt, dy by dt and dz by dt, what is this? This is actually the components of velocity, and this dx by dt will be denoted by vx, dy by dt by vy and dz by dt by vz. So this is simply minus vx square plus vy square plus vz square and plus 1. But the sum of the square of these three components will be equal to the resulting velocity v square, and therefore ds by dt whole square is equal to 1 minus v square. Okay. So now we have evaluated the value of this 1 minus v square in Galilean coordinates, and now let us substitute this value of 1 minus v square in equation number 2. Okay. So when you will substitute this value of 1 minus v square in equation 2, what will be your result? Rho will be equal to then rho 0 by ds by dt whole square, because 1 minus v square is equal to ds by dt whole square. And that's why you can say that this rho 0 is equal to rho times ds by dt whole square. Okay. So in this way we have expressed the proper material density in terms of its value in a moving frame. Okay, because we will consider that our matter is in motion. Now let us substitute this value of rho 0 in the defining equation of this energy momentum tensor, that is in equation 1. At the place of this rho 0, now we will write this expression. Okay, this expression defined in equation 3. So what now our equation 1 will become? You can see this will be T mu nu equal to rho times ds by dt whole square times this much. This is the last two factors are at each. Now this ds by dt whole square, this can be written as ds by dt times ds by dt. You can easily write. Okay. So our expression for T mu nu is now equal to rho times dx mu by ds times ds by dt times dx nu by ds times ds by dt. And you can see this ds and this ds will cancel out, this ds and this ds will cancel out, and we will get this T mu nu is equal to rho times dx mu by dt times dx nu by dt. Okay. Here you know this mu has value 1, 2, 3 and 4. Actually 1 stands for x coordinate, 2 for y coordinate, 3 for z coordinate, and this 4 for time coordinate t. Okay. Now if we consider that this u, v and w, these are the components of velocity. Okay, then you know dx1 by dt will be equal to u, dx2 by dt will be equal to v, dx3 by dt will be equal to w, and this dx4 by dt means dt by dt, which will be 1. Okay. In fact, here x1 stands for x, x2 stands for y, x3 stands for z. Okay. So this equation 4 in terms of these components of velocity can be written in matrix form. You can easily write it. This will be just a 4 by 4 matrix, and you can see how we can write it. For writing in matrix form, you can see when you will take this factor in first row, you will fix mu equal to 1. Mu equal to 1. Okay. And nu will run from, this nu will run from 1 to 4. Okay. It means this will run from x, y, z and t. So you can see how we can write it. The first element of this matrix will be rho u square. How we have written it? You can see that this is equal to rho times dx mu by dt. Okay. At times dx nu by dt. Okay. This is the expression. See here. Okay. Now we will take first of all in first term mu equal to 1 and nu equal to 1. So this will be dx1 by dt, and dx1 by dt will be equal to u. And this will be also dx1 by dt, which will be u. So u times u, this will be u square. Okay. So the first element of this matrix is rho mu square. Now, as I have told you, in first row you have to keep mu equal to 1, and nu will run from 1 to 4. Okay. So in second term there will be dx1 by dt. Okay. At times dx2 by dt. Okay. But you know this dx1 by dt is u, and this dx2 by dt is v. So this will be rho times uv. Okay. And in third term, you have to take nu equal to 3. And when you will take nu equal to 3, dx3 by dt will be equal to w. And therefore, the third element of this matrix is rho u w. And in last fourth term, again this mu will be 1. So dx1 by dt is u. But nu will be taken 4. And dx4 by dt, you know, that is equal to 1. You have seen dx4 by dt is 1. So the fourth element of this matrix in first row is rho u. I hope you have clearly understand. In the similar manner, in second row, you have to keep mu equal to 2 fixed, and nu again will run from 1 to 4. And in the similar manner, then you can see the first term will be rho times u times v. Second element will be rho v squared, third will be this much, fourth will be this much. So in this way you can write the energy momentum tensor T mu nu in matrix form. Okay. When you talk about the fourth row, again mu will be fixed at 4. Okay, mu will be fixed at 4, and nu will run from 1 to 4. Okay, 1 to 4. So in this case, dx mu by dt, this will be always equal to 1 in fourth row, because mu is 4. So dx4 by dt will be 1. So in the first term there will be, and dx1 by dt will be u. So this is rho u, rho v, rho w, and rho. Okay. So in this way, I hope you have clearly understand how we can express this energy momentum tensor in matrix form. Now, whenever you talk about a matter in motion, you know, matters are constituted by tiny particles, or you can say it is constituted by atoms. Okay. And if you will take even a elementary volume, let us say this is an elementary volume d tau. Okay. This will be a very small volume. Macroscopically, it is seen that this is just a microscopic volume. But even the volume is very small, but and the matter which is contained in this elementary volume will contain a large number of atoms, a large number of particles. Since the particle content even in this elementary volume is very large, so you can say that the particles contained in this elementary volume will have a widely varying motion, because number of particles is very large. Therefore, the terms in this equation number 5, this equation 5, must be summed up for varying motion of the particle. You must take under account the particles motion, and which are actually varying particle to particle. And for this, we must have to add to equation 5 the tensor formed by the internal stresses. An internal stress will develop which will affect the motion, and therefore, for get the correct expression for this matrix, we must take under account the change in the different element of this matrix due to the internal stress. So if you consider that this P alpha beta is the internal stress, okay, where alpha and beta both are actually x, y, z. Then for this atomically constituted matter, you have to add these internal stresses in each term. In first term, what will be the value of this P alpha beta? In first term, we will take alpha equal to x and beta equal to x, both equal to x. So the first term will become Pxx plus this much. Okay. In the second term, in, in fact, alpha will be in first row, alpha will be fixed at x and beta will run from x to z. Okay. So what the first term will become Pxx plus rho u square. But in second term, you have to take Pxy and plus rho ub. Okay. In third term, there will be Pxz plus rho uw. But the last fourth element will remain same because this alpha beta does not mean t, it means x, y, z only. Okay. So taking this effect of internal stress, the correct expression for energy momentum tensor in matrix form will become like this. You can see easily. This first element will be Pxx plus this much, second will be Pxy plus this much, third will be Pxz plus this much, and the fourth element remains at is. In the similar manner, in the second row, you have to fix alpha at y. Okay, but beta will run from x to z. So the first term will be Pyx, or you can write Pxy, okay, and plus this much. In second term, beta will be taken y, so this will be Pyy plus this much. In third term, beta will be taken z, so this is Pyz plus this much. So in this way, you can see these 9 elements will get changed, but the last row and the last column is unaffected. Okay, I think we have clearly understand. Okay, but you know, when the matter is in motion, only there is a transfer of mass from one region of a space to another. There is neither creation of mass nor destruction of mass. So mass remains conserved. Okay? Or in other words, you can say that mass is neither created nor destroyed. Or you can also say that there is no source and sink of matter. And therefore, the variation of this energy momentum tensor with respect to the position is zero. And therefore, you can say since no mass is created or no mass is destroyed, therefore, the partial derivative of this t mu nu with respect to the coordinate x nu is equal to 0. Actually, this expression represents the conservation of mass. Okay. So you can say that in absence of any external force, you can say. Now let us take mu equal to 4. We fix the value of mu at 4. Okay. And then we when you will take mu equal to 4 and use this equation 6, then what this equation 7 will give you? Let us see. If you will fix mu equal to 4, okay, it means you are talking about this last row or this last column. You can say last row, because you know in this first row mu is fixed at 1, in second row mu is fixed at 2, in third row mu is fixed at 3, and in fourth row mu is fixed at 4. So when you will take mu equal to 4, it means you are talking about the elements of this matrix only in this fourth row. Okay, it means then you can say that this T mu nu is simply equal to this much. Okay, and therefore when we will substitute the value of T mu nu, or the components of T mu nu are uh, rho u, rho v, rho w and rho, then this equation number 7 will be what? This will be del x here nu, when you will take nu equal to 1. Okay, nu equal to 1, it means x1, and x1 means x1 means x. So this will be del x rho u plus del x2, but you know x2 is written for y, so I have written del y rho v, and plus del rho w del x3, nu will be now 3, and x3 is equal to z, and lastly there will be del rho by del x4, but x4 is equal to t, so the last term will be del rho by del t, and that is equal to 0. Actually this is the well known equation of hydrodynamics, which is called equation of continuity. Okay, in fact the sum of these first three terms, can you say what is this? This is simply divergence of a vector rho v, capital V. Here capital V actually denotes the velocity vector whose components are u, v and w. Small u, small v and small w are actually its components, which can be actually, this will be Vx equal to u, Vy equal to small v, and Vz is equal to w. I have assumed. Okay, so instead of these first three terms, you can also write divergence rho v plus del rho by del t, and that is equal to 0. This is the well known equation of continuity in hydrodynamics, and you know this equation of continuity actually represents the conservation of mass. Okay, now we will see what will happen if we will take mu equal to 1. Just you have seen, when you have taken mu equal to 4, then T mu nu is simply equal to its fourth row, and therefore when you will take mu equal to 1, you have to think about the first row. Okay, instead of T mu nu, we will write the elements written in the first row. So in this condition, that equation will given as del pxx by del x plus del rho u square by del x. This is the first term, and this will be differentiated with respect to del x1, and the in second term there will be del xy by del y, because here differentiation will be with respect to x2, plus del y rho u v. See here, this is the second term, and in the third term there will be del pxz by del z plus del z this much, and last term is del t rho u, and that will be equal to 0. I have substituted this in this equation number 7. Okay. Instead of this T mu nu, you have written the elements defined in the first row of this equation 6. Okay. Now you can write this expression in this manner. We keep the partial derivative of this internal stresses in left side, and the remaining terms are written in this right side with negative sign. Okay. Now you can simplify this RHS. You can see the form of the equation and you can easily simplify. This equation can be written as minus u has been taken as a common factor, del x rho u plus del y rho v plus del z rho w plus del rho by del t. And minus rho is now taken as common factor, u times del u by del x plus v times del u by del y plus w times del w by del z plus del u by del t. But see this expression inside this first square bracket. You have just seen that this is equal to 0. This is equal to 0. So when you will make the use of the equation of continuity which you have obtained in equation 8, you can easily say that this quantity is 0. Therefore, in RHS, we are left only with these terms in the second row. That is minus rho times this much. This remains only. Okay. And therefore, you can write it minus rho u times del u by del x plus v times del u by del y plus w times del u by del z plus this much. Okay. Now we consider that this differential operator u times del x plus v times del y plus w times del z plus del t is equal to d dt. Okay. This is equal to d dt. Therefore, the sum of the terms inside this square bracket can be written as du by dt. Okay. And therefore, we get del p xx by del x plus del p xy by del y plus del p xz by del z is equal to minus rho du by dt. In fact, this du by dt is what? U is component of velocity in x direction. So du by dt is the component of acceleration in x direction. Okay. Now in the similar manner, when you will take mu equal to 2 and mu equal to 3, then you have to take the second and the third row of this matrix T mu nu, and that will be substituted in equation 7. I have not done that algebra. That can be written on the basis of analogy. You can see when you will take mu equal to 2, instead of u there will be v, and when you will take mu equal to 3, instead of u there will be w. So you can easily write on the basis of this equation 9a the expression for this del p yx by del x plus del p yy by del y plus del p yz by del z equal to this much, and del p zx by del x plus del p zy by del y plus del p zz by del z equal to this much. Okay. And as I have told you that this du by dt, du by dt and dw by dt, these represent the components of acceleration in x, y and z direction. Actually, the equations defined in equation number 9, that is 9a, 9b and 9c, these are also the well-known equation of hydrodynamics. If you have studied hydrodynamics, you find such equations there. In fact, these equations defined in equation 9a, 9b and 9c are well-known equations of motion in hydrodynamics in the absence of any external force. When no external force is applied, then such equation exists. Actually, these equations represent the conservation of momentum. It means in absence of external force, the linear momentum of the matter remains conserved. Okay. So equation 9 is nothing. These are actually the mathematical statement of the conservation principle of momentum. Okay. So I have written here, you can see that equation 9 are valid in absence of any external force field and represent the conservation of linear momentum. Okay. Now we will learn something more about this energy momentum tensor. You have seen earlier when I have discussed actually the Christoffel symbol. Okay. Then you know when we write the Christoffel symbol in Galilean coordinates or local inertial coordinates, then you know its value is 0. So this gamma sigma mu nu is equal to 0. And therefore, when we will take the covariant derivative of this energy momentum tensor T mu nu with respect to x nu, then that will be simply equal to the partial derivative of T mu nu with respect to x nu, because this gamma is 0. Okay. So taking this fact under account, you can easily say that in Galilean transformation, in Galilean coordinates, this equation number 7, which I have written here, this equation 7. Instead of this equation 7, you can write this much, because del T mu nu by del x nu is equal to the covariant derivative of T mu nu with respect to this. Okay. And you know the covariant derivative of this second rank tensor is simply its divergence. So we can write that covariant derivative of T mu nu with respect to x nu is 0. Or in other words, we can also say that this equation implies that the divergence of this T mu nu is 0. And when you say that its divergence is 0, what does it mean? In fact, this del T mu nu by del x nu, or the covariant derivative of T mu nu with respect to x nu, this actually represents the rate of creation of mass and momentum in a unit volume. Okay. But no mass is created, and therefore its value is 0. Okay. Now, in several problems, it is convenient to use the mixed tensor, this T mu nu, instead of this contravariant tensor. In the beginning of my lecture, I have told you that this energy momentum tensor may be in covariant form, may be in contravariant form, or may be in mixed form. You have also learned when I have discussed the different tensors and different process of calculus in dealing with the problem of tensors, then you have seen, particularly in Galilean coordinates or the local inertial coordinates, this T mu nu is given by minus g mu lambda times this contravariant tensor. Okay. That is, if you talk about T12, then this will be minus G22 T12, and that will be equal to simply minus T12. Okay. So on this basis, you can write this T mu nu, which is equal to minus this T mu nu will be equal to minus T mu nu. Okay, minus T. And so when we will now define this T mu nu, the sign of this T mu nu will be only changed, and therefore this first element, which was earlier pxx plus rho u square, now it becomes minus. This is also minus. Sorry, here there will be minus sign. Okay, and in this manner you can write the elements of each row and column. Okay, so you can see that from equation from these equations it is clear that the scalar density of matter, which is denoted by the symbol rho, is one of the components of the second rank energy momentum tensor. Okay, so in this way I have presented the basic concept of energy momentum tensor, particularly in absence of any external field. But as I have told you, in our forthcoming videos, whenever needed, we will also talk about this energy momentum tensor in presence of the external field. Okay, and I think you have clearly understand each and every step of this lecture. Okay, thank you very much.